hear this if you want to.
Do we need to add the course?
Yep. So you have to add the course, and you also have to have your remote registered under that iClicker account. And that's what you should have got my email to hit that join course link. I can resend that to you after class because, like I said, I think you're the only one that isn't registered for the class.
Well, I just looked it up on the thing. It has ECON 21 honors.
Yeah. Yep. You can just click on that one. So today, kind of before I forget, I'll mention at the end of class as well. Instead of iClickers today, I'll put up an online quiz. I'll have a couple questions that'll go over what we go, the material that we cover today. Just to kind of get an idea of how much you guys are understanding, kind of change the direction of what we're going to talk about Wednesday and Friday. Should be getting those Excel assignments. You should start seeing grades pop up this afternoon and tomorrow. I'll start getting those graded. That Connect assignment, right? We push the due date to do at the end of the day today. We covered all the material for it. I mentioned questions, I believe it was 13 and 14. And it might already show up that you can award full credit for those because they had that kind of NAD question in there that we didn't cover that statistic. So I said you don't have to worry about that. Okay. I will get the next Connect assignment up there likely tomorrow. So after this due date is passed, I'll get the next one up there so you can start working on that. It'll begin with kind of the material we start covering today. All right, and that'll be due 2 weeks from today. And then I'll also probably after Wednesday, we should do some Excel work Wednesday in class. If not Wednesday, Friday for sure. I'll then get the next Excel kind of assignment up there. And that'll kind of line up with what we cover this week in Excel. Okay, so you should see those next two pop up. Because the Connect homework is going to pop up there first, I would suggest kind of start chipping away at that as we cover material throughout this week. Okay. Any other questions for me before we get going? Okay. So, kind of just barely introduce the idea of probability, just kind of as a concept, right? We have this experiment, right? We're running something. This could be as simple as asking somebody a question, right? I ask you, what is your height? I don't know. Well, I know the range of possible values that you could respond with, but I don't really know if I select someone at random what their height's going to be, right? So I've got this experiment that I'm running with an uncertain outcome. So probability is going to be the measure of once we carry this experiment out, how likely are certain outcomes, right? So we know that if I chose a person at random, it's much more likely that they're 5'8" than they are 7'3", right? I know that there's all these different outcomes, but they have different likelihoods of occurring. Okay, so usually we're thinking about one specific outcome as our event, right? We're interested in the probability that when I select someone at random that they are X height, right? But it could be, well, what's the probability that they're somewhere in between 5'3" and 5'10", right? So my event can include multiple outcomes as well, and we can come up with a probability of seeing something within a range of these possible outcomes. So if we're thinking about these events, right? It doesn't matter if it's one outcome or a collection of them. We'll kind of write the probability of the event as P and then in parentheses, whatever that event is. Usually this will be a word or that the variable is equal to a certain value. Like kind of depends on the experiment that we're running, right? But the probability of some event. Okay? So if I think about this as simple as a 6-sided die and I roll it, right? I can see 1 through 6. I've got 6 possible outcomes. And there it's kind of an easy roll because every single outcome is equally as likely. Right? But no matter what the experiment is, if I think about the probability of seeing a certain event, at the very lowest, it could be what? So if I say rolling a 6-sided die 1 through 6, what's the probability of getting an 8? There's not an 8 on a 6-sided die, right? So what's the probability of getting an 8? 0, right? That's the lowest possible probability you could ever see. If I did something like, I flip a coin, what's the probability that I see heads or tails? 100%. We're dealing with probabilities. You said probabilities are like percentages, but in decimal form. So the highest probability you could ever see is 1. Now, if we think about this 6-sided dice example again, if I take the probability of getting a 1, and I add to that the probability of getting a 2, plus probability of getting a 3, all the way up to the probability of 6. If I add up the probability of every possible outcome, that should always add up to 1 as well. Right? You go with the 1/6, right? Well, I've got 6 outcomes, each probability of 1/6 of occurring. I add those up, that's 1. So it should be that this probability we see range somewhere between 0 and 1, right? It shouldn't ever be outside of that range. And they should always, if we look at the probability of every single event, those should always add up to 1. Okay. Should be pretty straightforward, not too bad. So what does this kind of look similar to what we were doing before? This should start, like some of the stuff we're talking about should look very similar to relative frequencies, right? We said relative frequencies always add up to 1, and they have to be somewhere in the range of 0 to 1 as well. So how do we figure out what these probabilities are? So I'll go through this pretty quick because this isn't really, I mean, generally we're like told what these probabilities are, or in practice, we generally only use the empirical method, which I'll kind of get to in a second. All right, for my example of like rolling your dice and that's 6 sides, you know, every single outcome is equally as likely, right? So you had the probability of 1/6. What did you do in your head there? You just took the number of possible outcomes, I'll call that n, right? And then if everything's equally as likely, 1 over n, all right? If I'm talking about flipping a coin, I've got heads and tails, I've got 2 possible outcomes, the probability of each outcome would be 1/2 or 0.5. If I have 100 possible outcomes, the probability of every possible outcome would be 1 over 100, right? So the classical method is pretty easy. And then the other two will go into a little bit more in depth, which is the empirical and then the subjective method, okay? Don't worry about running this down to the slide for each one of them here. We'll kind of talk through them. So this classical one, really pretty basic, right? I just take the number of possible outcomes I can see, and if everything is equally as likely, the probability of each one of those outcomes would be 1 over n, 1 over this number of possible outcomes that I have. So if I flip a coin twice, right, and flipping a coin once is pretty easy. Probably getting a heads would be 0.5, probably the tails would be 0.5. If I flip it twice, what are the different combinations that I have? Right? Well, I can get 2 heads in a row, I can get a heads and the tails and a heads, or there's 2 tails in a row. So I've got 4 different possible combinations. So what would the probability of any one of these combinations be? There's 4 possible outcomes, each one, yeah, 1/4, right? Or 1 over n. So all you do is take the number of possible outcomes that you have, and 1 over that would be the probability of any one outcome if everything's equally as likely. Now this applies to things like flipping a coin, rolling a dice. Honestly, not the most interesting of examples. So in practice, it's probably going to be a little bit different. Right? This kind of applies to some of our real basic examples, but generally we're going to have to use this empirical method. So the way the empirical method works is, you know, maybe I have this experiment and I have no idea how likely these different outcomes are. Some are more likely than others, but I have no idea. Right? So what I'll do is I'll run this experiment a bunch of times, right? So just keep repeating this experiment over and over, and I just start recording the outcomes, right? So the example I can kind of toy example is like you ask somebody what their favorite cuisine or what their favorite food is, right? So if I'm asking someone at random what their favorite food is, I know it's Mexican or Italian or all these different, you know, Greek. And maybe certain types of cuisine are more popular than others, right? But I don't know what those probabilities are. Like, you know, maybe 50% of people would choose, you know, Mexican cuisine. I don't know that, right? So what I'll do is I'll start asking people what their favorite cuisine is and start recording it in this huge data set, right? So, you know, maybe I ask 60 different people or 60 different students, right? And I start recording every single one of their favorite types of food. And then look at my data set and I see, okay, out of these 60, 15 of them responded with this one specific outcome, which was Mexican food. Well, if I'm then going to ask another student at random, right, after I've asked the initial 60, what's the probability that that new person I'm asking responds with Mexican food? Well, if my sample is good, right, and we'll talk about kind of sampling issues down the road, I'm making sure we don't have a biased sample. Well, I look at my data set and I say, well, of the other times I've run this experiment, 15 out of 60 times, I saw the response of Mexican food. So if I ask somebody at random, the probability they'll respond to Mexican food from my data, I can assume is 15 out of 60. And maybe only 5 people said Greek food. There's the probability that if I ask someone at random, what's probably to respond to Greek food to this survey question? 5 out of 60, right? I'm just using past experiment outcomes to assign these probabilities, right? And that's generally what we'll do, right? We'll look at whatever the experiment is, look at past instances of it, look at the outcomes, and then assign our probabilities this way. This might make a little more sense, like I said, Wednesday or Friday, once we start looking at Excel, we're doing some actual data, and we can actually come up with these probabilities. Okay. Any questions on this? This shouldn't be too bad. So the subjective method seems like it's kind of hokey, but basically you just, from your own experience or your knowledge, you assign the probabilities, right? So a good example of this, or at least I think a good toy example of this is, let's say a company is going to choose a CEO. We've got 4 candidates, right? So would it make sense for me to use the classical method where I assign that every single person here is equally as likely, right? Every candidate has a 1/4 chance. Well, if candidate Andy is like only ever been a janitor, I doubt he has a very high probability of being selected as a CEO. Rankin has been a CEO in the past, maybe a CFO in another company. There's probably a much higher probability that the company chooses that candidate. So this would be a situation where, you might consult industry analysts or people who are very familiar with whatever this company does and said, and these people's kind of resume and say, well, look, right, based off of what they've done in the past, we know that Hill is the most likely person who's going to get chosen. This is kind of like when you think about anything we were applying for something, right? Can't run that experiment over and over, right? So think about this one. Why would I use the empirical method? Well, I can't run this job search 60 times and look at who the company chose 60 times. In practice, this is happening once, right? And it's happening, only this one time. So we won't have any previous data, right? So it seems like we're kind of making it up, but in certain situations, the subjective method is the best that we can do. Okay. So welcome to probability statistics, class where everything's made up and the numbers don't matter. If you've never seen Whose Lines Anyways, actually just saw, first of all, it's like only one of the original guys, but they're doing like college tours or something where it's Ryan, is it Ryan Hill, the real tall, goofy guy on it? It's like the only one left. Anyways, Google Whose Lines Anyways. It's a hilarious show. Stuff like that should still be on TV. But I digress. So we've just got this kind of general setup of we're going to be assigning these probabilities. Once we have these probabilities, how do we start making some decisions? Okay. So we'll get a little bit of notation out of the way, and then we'll start thinking about things with Venn diagrams and something we'll call contingency tables. So I think to do this, I'll kind of walk around this little example as we walk through this. So let's say, really today is going to be the only time I write things down in set theory. It'll be very simplistic. I won't expect you to know a lot, but I think you can just kind of get the idea as I go through. So let's say I've got this 6-sided die, right? So I know I can see 1, 2, 3, 4, 5, or 6. Okay, those are all my possible outcomes. So let's say my event A is that I see 1, a 2, or 3, right? Those are all the outcomes that are in my event A. Remember, events are subsets of the entire experimental outcome space. So the entire space would be 1 through 6. Here's a subset, right? When I have the complement of an event, the easiest way to think about it is it's everything that's not in that event, right? It's not the most technical way to talk about it, but it's everything that's not in event A. So if I'm thinking about this 6-sided die, what would be my event A complement? Yeah, just the other possible outcomes I can see when I roll this dice. So it's not too bad. So if I think about then, I want to think about the union of 2 events. Well, I've only got 1 event here, so I need to come up with, well, what's event B? Right. So let's say event B is, make this a little bit harder. Right. 2, 4, and 6. Okay. Well, first of all, what would B complement be? Everything that's not an event B. So what would my outcomes in B complement? 1, 3, and 5. Okay. Any questions on that? So actually, I think I'm going to jump ahead. And I think we'll actually do the intersection first, and then we'll come back to the union. So if I looked at the intersection of 2 events, we write this with like what looks like this upside down U. Okay. So this is set notation. I always say that like another way to think about this, people say the intersection, you can think about it, it's what's in A and in B. So if I drew a line through it, it looks like an A. So this upside down U kind of reminds you, you're looking for what outcomes are in both event A and in event B. All right, so what's in A and in B? So I look at events A and B. What would be the intersection of these two things? Yeah, see someone saying the only outcome that's in both of them is 2. So we can think about the intersection, we write it with this upside down U. Some ways, I guess some people think the good way to remember that is it kind of looks like an A, put a line through it, so it means A and B or A intersection B. Like I said, this right now is trivial, and we'll kind of put this in the context of a contingency table. These things become a little more interesting when we're talking about the intersection. So what about if I want what we call A union B, right? Or what we call A or B, right? So this is all the outcomes that are in either event A or they're in event B, or they could be in both, right? But it has to be in at least one of them. So here, if I'm looking at A and B, what would my outcomes be for the union of those two events? 1, 2, 3, 4, 2. 1, 2, all right, so 1, 2, 3. Well, 2 gets repeated, so it's only one outcome, so don't write that down again, right? It's the outcome of 2. And then the other 2 outcomes that I can see in event B would be 4 and 6. Okay. Any questions there? So I've got the intersection is what's in both of them, and then the union is what it could be in A, it could be in B, or it could be in both. So it kind of gets pretty big pretty quick, right? Depending on what examples we're looking at. Now I'm gonna punt a little bit on this explanation until we work through some more material. But the other notation that we'll want to know for down the road this week is what we call a conditional, right? Or a given, right? So the way that we read this is A given B. Okay. So we're not dealing with probabilities yet, but we're thinking about what are, given that I know I have an outcome that's somewhere in event B. So if you tell me like basically B has occurred, right? I know that event B has occurred. So I know that the outcome was either 2, 4, or 6. But I don't know which one, right? I'm just being told that event B happened. So I know either 2, 4, or 6 happened. Well, here, what's the only outcome that's in A? Right? If I say that I'm telling you B has occurred, well, what's the only outcomes left in A? Well, if B has occurred, the only one of those outcomes that are still in event A would be 2. Right? So in this situation, in this example, the intersection is the same as the conditional, but that's not always the case, right? In a little bit more of a goofy example, but also maybe it makes the conditional make a little more sense. Let's say event A is that I slip and fall walking into the building, right? Or maybe like one of my favorite pastimes. Let's say slip and fall getting off the bus to go to class, right? Well, that probability is pretty low, right? I don't slip and fall very often just walking into the building, right? Or getting out of my car. But let's say event B is that there's freezing rain outside. Well, if I tell you, given B has occurred, that there is freezing rain outside, what do you think is happening to the probability that I slip and fall? Or event A goes up, right? So that example, you can kind of start to think about, oh, when I have kind of these conditions, right? When I know this other event has occurred, well, now the probability of A might go up or might go down, right? So that's eventually what we'll get to. Like I said, with just kind of dealing with this simple dice example, it's not as obvious, but thinking about just that when I'm told something else has happened, it could change the probability of other events. That's the idea of a conditional probability. Okay. So we'll kind of focus on those first 3 to start out. So these are just nice visuals. Have you guys seen Venn diagrams before? I feel like science classes like to use these in high school and stuff. So basically, I've got this huge rectangle, which is every possible experimental outcome. Okay. So you can think about here, right? This would be like, if I partition this off into different sections, one of them would represent the outcome of rolling a 1. One would represent the outcome of rolling a 2, 3, 4, 5. It's every single possible experimental outcome. Then my circle A is all of the outcomes that are in my event A. And then circle B, no, over here, is all my outcomes that are in event B. Right? Then what would the intersection look like? Well, basically, anything that's in circle B, but also in circle A. So visually, where do those two things overlap? Right? I mean, kind of visual with these numbers here, where would A and B overlap? Well, it's only that outcome of 2. Okay? And then the union of 2 events is basically anything that's in A or anything that's in B, or it could be in both. So it's basically we just shade in the entire region of both A and B, right? Or with the numbers, right? 1, 2, 3, 4, or 6, right? It included the outcomes of 1 and 3, which were in event A, but not in B, right? So notice 1 and 3 are in event A, but they're in B complement. So that would be kind of like, actually, I had 2 sides of this stuff. I'll try to give you a visual of this and kind of break this down. This might become useful later too. So this is event A, right? What would everything outside of that circle actually represent? Yeah, everything not in A, right? So A complement. Okay. And then think about if I've got event B here. Everything outside of B, actually I probably could use a different color to kind of help with this. So let's say circle B is red. Here is circle B. Everything that's not in circle B would represent B complement. So if I think about the union, I can actually kind of break this down to 3 components. So I'm going to write this up here. If I think about the intersection of these 2 events, kind of like everything that's in circle A, but not in B, right? So this like crescent moon over here, right, would represent everything that's in A and not in B. So we can kind of think about that's the first kind of component here. We're not doing probabilities yet, but you can kind of imagine if I just take that space. Well, then what does this crescent moon kind of represent? Well, that's everything that's in circle B, but not in A, right? Outside of A. So this crescent moon would be everything that's in B, but not in A. So everything that's in B, but not in A. And then what's the third component that we need to fill out the union? Well, what's in both of these? Well, what's in A and B? That's literally just our, no, sorry, plus sign over here. Basically just our intersection, right? What's in both A and B, right? And that would fill out this entire space, right? So you can think of the union as just, right, somewhere in either one of those circles. But for some of the things we'll talk about later, you can also break that down really into 3 components, right? Everything that's in A, but not in B, everything that's in B, but not in A, and then everything that's in both. Okay. Questions on that? Or keep moving here. So, kind of some nice visuals, but unfortunately we have to deal with some numbers, right? So the way that we kind of depict this, or at least we'll start depicting it, is through some pretty simplistic contingency tables, okay? So the way that we want to read these contingency tables are get the probabilities of the events themselves. So the probability of A, the probability of A complement, probability of B, probability of B complement. We just go down to these total columns or rows, right? So probability of A would be 0.6, okay? So you can kind of think about probability of A is just this total. How are we coming up with this total, right? Well, for now, I'll kind of give you a nice visual later, but for now, just think about it as you're going to add across the rows to produce those total columns. So even if I didn't show this to you, you could come up with a probability of A because the probability is in A and in B, plus the probability is in A and not in B. Let's just every possible thing that's in A. So if I add across the rows there, I could reproduce those total columns. So 0.4 plus 0.2 is 0.6 plus, I can do the A complement, 0.1 plus 0.3 will be 0.4. I can also reproduce those totals at the bottom by adding down my columns. Right? So 0.4 plus 0.1 gives me 0.5. That's just the probability of B. I wanted the probability of B complement, well, that's just 0.5 as well. So I can add down the columns or across the rows to reproduce those totals. I'll show you why that works in just a second. I'll go here first though. So we've got those kind of total columns, right? Then the contingency tables, the 4 top left cells, these all represent intersections. Okay? So if I'm thinking about what is the intersection of A and B, I'll go to event A, event B. The probability of the intersection of those two things would be 0.4. What if I wanted the probability of A complement and B complement? Well, probability of A complement and or intersected with B complement is in this cell right here with 0.3. So those top 4 left cells represent the intersections of whatever the row and column headings are. The totals just represent the probabilities of whatever that row and column heading is. So it doesn't matter which way we write this. This is kind of our first probability law that if I say what's the probability that I'm in A and B, it's the same as I'm in B and A, right? Thinking about this is like what's the probability that someone's over 6 feet tall and makes more than $50,000? Well, that's the same as the probability they make more than $50,000 and they're over 6 feet tall. Right? It doesn't matter how I say it, I'm still talking about the same thing. Okay. So I want to produce or provide a little bit of insight as to why I can add across the rows or down the columns. So go back here for a second. Let's think about, I've got event A here. Okay. I then have, use my other color. Let's say, here's my event B. And then if I shaded this area in, which I'll just kind of use these like lines to kind of represent that. These lines represent everything that's not in B or B complement. Okay. So we know visually the probability of A, this circle of A is, or sorry, the probability of A is just represented by this circle, right? So this would represent the probability I see an outcome in event A. Okay. Well, I could break that up into 2 components, right? The first component is, here's all my outcomes that are in event A, but not in event B. So that kind of black shaded area would represent what? Everything that's in A. So the probability that I'm in A and not in B or in B complement. Okay. If I then think about, well, what's the other part of this event A that I'm interested in? So this green shaded area would represent what? Everything that's in circle A, but also in circle B. Right? So if I add these 2 components up, what do I have? I just have the entire circle A, right? Or the entire probability of A. So that's why to reproduce this total, right? To get the probability of A, I'm going to take the probability of A and B. Here, I'm going to add to that the probability that in A and B complement. That was our other component, and that should just add up to that total, that probability of just the event itself. Okay. You can kind of think about it this way. What's the probability if I chose somebody at random that they make more than $50,000? Right, that there is some probability that exists there. Right, I could then break that down to, okay, well, the person either makes more than $50,000 and is over 6 foot tall, and then add to that the probability they make more than $50,000 and they're 6 foot or shorter. That includes every single possible height, right? So that should count every single person that makes more than $50,000, right? That first event A I was interested in. So these are all just different ways of thinking about what we're looking at. So you get a visual, we kind of have the contingency table where you can just think about, really, the contingency table breaks this down to 2 components. So I can add across the rows to reproduce the total, or kind of these examples where, you know, if I'm counting everyone that makes over $50,000, they're either over 6 foot tall or they're under 6 foot tall, right? So those, you know, if I count everybody in those two groups, that's just everybody who makes over 50,000. And that, you know, I was using A and B being, the outcomes we see in a dice, but it could be things like, does someone make over a certain amount of money? Does somebody, have under a certain number of years of education, right? These events could be really a variety of different things, okay? Any questions here before we keep moving? So we've got the intersections, kind of talked about breaking these down into two components so we could reproduce those totals. Order doesn't matter for the union or the intersection. So I think I actually accidentally gave you an intersection example earlier for this slide. I didn't realize that I started with the union first, but basically, right, it doesn't matter if I'm looking at intersections or unions, the order in which I say it doesn't matter. Okay? And that's kind of visually, you can see it too, right? Like if I want A union B, well, that's everything in circle A or in circle B. If I want B union A, it's everything in circle B or circle A. Doesn't matter what order I say that. This is always good, right? So if we're thinking about the intersection, right, we say it's fine, it's actually fine, almost no intersection there, right? So we'll start to kind of deal with things where that probability of being in multiple events could be pretty large, but it could also be pretty small. In fact, sometimes, I'm going to jump ahead here, right? We've got events that we will say are mutually exclusive, okay? So I'm going to jump ahead a little bit here. But let's say I've got two events, and I'm thinking about they can't happen at the same time. Right? So what would that look like visually? Okay, so if they can't happen at the same time, that means the intersection is zero. Right? That would be something like, could I be, I don't know, over 200 pounds and less than 150? I mean, no, there's no number that fits both those categories. So I know the intersection of those two events would be zero. Now, visually, what would that look like? Basically, two circles that don't overlap. Okay. And then on top of that, what would it look like in the contingency table? What would have to be that the intersection is zero, so it would have to be that when I looked at that top, one of those top four left cells, the intersection of A and B, I actually have to see a zero there. Now, we won't deal with a lot of examples like that because they're not very interesting, right? I mean, if I already know they're mutually exclusive, I know the probability they occur at the same time is zero, there's not a whole lot of interesting examples that we can kind of use there. And I'll come back to this because we haven't talked about this, so don't worry about this line. I just want to skip ahead because I started to kind of think about that this intersection can be very high, it can be very low. In fact, it can be as low as zero if there's no overlap in those circles. All right, so we'll go back. Here we go. So this complement rule, excuse me, basically says, right, if I take everything that's in circle A there, or think about that circle represents the probability I see an outcome in event A. Okay. Well, A complement is everything outside that circle, right? So if I add the probability of A complement to that, what should those always add up to? 1, right? When I think about everything not in A, I add that to A, well, that includes every single possible outcome, right? So this would be like saying, what's the probability somebody makes more than 50,000 plus the probability they make 50,000 or less. Well, that's every possible income. So these always should add up to 1. If I rearrange that a little bit using algebra, I get my nice complement rule up there, right? So what I solve for here, so I'll subtract the probability of A from both sides. Now I've got my complement rule. Anytime you tell me the probability of an event, you automatically know the probability of its complement. If I tell you the probability that if I chose somebody at random, they're, I don't know, for the, what's a good number? So probably that they're older than 40 is like, I don't know, 0.6. Well, what's the probability that they're younger than 40 or 40 or younger? Well, 0.6, right? That probability would be like 60% of people are older than 40. That means 40% of people are younger than that. So not too crazy. And this will help us out in some things that we're going to do kind of down the road as well. Okay. Any questions here before we keep moving? I kind of remember visually the reason why we know that this white and blue area add up to 1 is the entire experimental outcome space is every possible outcome. We said if we added the probability of every possible outcome, it was always add up to 1, right? So you kind of think about it as the area of your rectangle. If you're drawing this out visually, if it helps you to kind of have a visualization, the rectangle, the area itself is 1. And then maybe the area that's here is A, maybe the probability of A is 0.4. Right, so it's gonna always represent a smaller subset of the entire experimental outcome space of one. All right, so the addition rule, maybe a little bit tougher. Let me think how I want to explain this first. There's two ways we can think about this. I think I'll break this down. Well, I'll just show you. Okay. So if I want to find the union of two events, right? What's the probability it's in both A or it's in B, right? It could be in one, could be in the other, could be both. Well, if I simply added the probability of both events up, what would happen? So if I took the probability of A and I added to that the probability of B, what have I done with everything that's in the middle? I've actually double counted it. Yeah. Kind of think about that dice example, I would have counted 2 twice. Well, it's only one outcome, right? So because I've double counted the outcomes that are in both of them, I need to subtract them out once to make sure I only counted them one time. So what's in both of them? That's just the intersection. Right? So to get the union of two events, being A or B, I'll add up the probability of both events and then subtract out the probability they're in both, or subtract out that intersection. Okay. Any questions up to this point? Okay, so I can kind of also think about if I broke this down into different components. Here would be like, let's say I just wanted this crest to go. Okay. Well, how could I get that? Well, if I took the entire circle of A, or the probability of A, and then I subtracted out the intersection, I just have this crescent. Right? If I then wanted just what's in this kind of crescent, well, that's everything that's in B, so the probability of B, but then subtract out what's in both. So I've now got these two kind of crescent moons here. I need to make sure I add back in what's in both, or the intersection. You can kind of see here, I've got the intersection twice and subtracting, I'm adding it once. So one of those, two of those cancel, and I'd be left with what I showed you in the previous slide. There's another way of thinking about it. I think the idea of thinking about both the circles and I double counted it, so I'll subtract it out once, that always connected with my brain a little bit more. But if you wanted to, kind of try to come up with what's in each of these 3 areas, you could do that as well. Any questions then? Okay, so 2 different ways of looking at this contingency table and coming up with unions. So the first way is to add up the probability of each event and then subtract out what we double counted, right? So really all we're saying there is the probability of A union B, or remember A or B, is take the probability of both events and then subtract out the intersection because we would have double counted it. Well, how can I do that using this table? Here, what would the probability of A be? I said those total columns just represent the probability of the events themselves. So the probability of A is 0.6. What's the probability of B? 0.5. Oops. And then what's the probability I'm in A and in B? Well, those top 4 cells represent my intersections. So the probability I'm in A and B will be 0.4, right? So subtract out that 0.4. Okay. Now notice there's a lot of overlap with event A and B here, right? 0.4 out of 1, I mean, relatively large. If I forgot to subtract out what I double counted, if I just add up the probability of A and B, what do I get? 1.1. How do I get the probability of something happening over the 1? I know I made a mistake. Oh yeah, I forgot to subtract out what was in both. Okay. So this would be what? 0.7. Now earlier, I broke this down into 3 components, right? So we had, this was everything that was in A and not in B. I guess I should probably put labels on these, right? Everything that was in event B and not in A. And then in the middle here, that was the probability that I was in both of them, or the intersection. So I had that, we kind of did that earlier. You break this down to these 3 different components. Well, how could I find each one of these, add them up to get the union. Well, got my contingency table here. I think this is what we just did. But what if instead I wanted the probability of A and B complement? What would that be up here? Probability I'm in A and B complement, 0.2. Right? So this is 0.2. What's the probability I'm in B and A complement? So the probability I'm in B and A complement is 0.1. And then we've already done this one, but what's the probability I'm in both A and B, or the intersection of A and B? What was that top left cell, which was 0.4. Now notice if I add these three areas up, I get the exact same thing as doing it the other way. Okay. So visually what that looks like, this is like not a technically good way to remember this, but if I want the union of two events, if I just go to the intersection and make like an L and then add those up, it'll work for me every time. It's not a good way to remember how to do it. Rather, if I wanted, like, let's say the union of A complement and B complement, I'd go to the intersection, make an L, and add them up. Now, probably what is a better way to learn what the union of two events are and to use this contingency table is to go back. There we go. And use this method because it kind of lines up with what that addition rule actually is. And for me, I was easier, like, it's easy to get these total probabilities. Like I said, I don't have to worry about thinking about, okay, what intersections might just go to the total columns, grab the probability A and B, and then I only have to find one intersection and subtract it out. But both ways should lead you kind of to the same answer there. Just different ways of thinking about it. Okay. Any other questions there? So we kind of talked about being mutually exclusive earlier. Now we have this addition rule. So what's really nice about mutually exclusive events? Well, if I want to come up with a union, if they're mutually exclusive, the intersection is just 0. So there I would just have to add up the probability of event A and the probability of event B, and that's my union. There's nothing I double counted. There's nothing that's in bold. So with mutually exclusive events, finding the union of two events is actually a little bit easier. Questions there? Not sure what questions that's there. Pretty easy. Okay. So I think, you guys are probably too young now, but back in the 90s, phone internet access were mutually exclusive events, right? You had one phone line, you could either be using internet or you could be on the phone. This got me in a lot of trouble in high school, right? Because people kept getting busy signals. I know now we don't even know what busy signals are, but like what they used to exist, right? So I've got mutually exclusive events, makes our addition rule a little bit easier. Okay. We can also break this down one step further. And this is where I'm not going to necessarily expect you to reproduce this last component, which is the intersection of the complements. But I'll give you, I'm telling you here, this shaded blue area does represent the intersection of the complements. So let me give you, just those of you who are curious, and also I don't like telling people things without providing some evidence here. So this is my event A. Here is A complement, right? So the shaded area is A complement. If I then take circle B, everything that's not in B, it's in kind of this shaded red area. Well, the only place where I have this shaded red area and the shaded black area is everything outside of these two circles. So everything outside of these two circles is where I see the intersection of my shaded black area, A complement, with my shaded red area, B complement. So if that's where those two things overlap, everything outside my circles or outside of my union is the intersection of the complements. So it's basically everything that's not in my event A and not in my event B. I'm gonna go back a little bit, I guess, kind of trying to connect everything here close to that. Let's see if I can remember the numbers I gave you. So this was what? 1, 2, 3. This was 2, 4, 6. So my complements were 4, 5, 6. And complements here, what, 1, 3, 5. So notice, if I do the intersection of my complements in that dice example, it's everything that's in A complement and B complement, which were what? So 5 is the only thing that's in both of these, right? Which notice that should be, from my visual, everything that's not in the union. Well, what was the union of these two events? We said that was 1, 2, 3, 4, and 6. So these are all my outcomes that are in the union. Everything outside of that union, that blue space, should be the intersection of the complements. Sure enough, the only outcome not in my union here is that value of 5, which was the intersection of the complements. So you can prove this to yourself with actual outcomes, or you can just remember like everything in this blue area is just the intersection of my complements. And from here, we could break this down a little further. Well, what is in both of my events here? That just represents my union. So I know that the union of two events plus everything outside of them, that blue area, that fills out my entire integral outcome space. So I know those two things have to add up to 1. The union of two events and then the complement, the intersection of the complements of those events, have to add up to 1. The white area plus the blue area fills out my entire experimental outcome space. So they have to add up to 1. Well, from there, I can use my addition rule to break down my union into other components. We said the union is just take the probability of each event, add them up, and subtract out that intersection or the thing I double counted. So if I substitute that in there, now I've got this equation where I can kind of break down this experimental outcome space into these 4 different components, and I know they have to add up to 1. And right now, it might not seem like this makes a lot of sense or is that helpful, but once we get to some actual examples, this will be useful. Okay. So we'll pick up on this next class. We'll kind of walk through some examples. I might ask you to do one. We're then going to talk a little bit more about conditional probabilities and then transition into Excel. So you'll probably see another in-class data file pop up there on Canvas, because we'll probably, if we do start working with at the end of class, I will make sure it's up there so we can kind of work along. Okay. Other questions for me? So what's due by the end of the day today? Next assignment. If you see the next ones pop up, feel free to start working on those. But it'll be kind of covering this probability stuff we start talking about today. Okay.
Quiz before Thursday, I mean Wednesday.
Yeah. So